Um, I will be presenting the Ketterle 1995 paper on Bose-Einstein condensation in gas and sodium atoms. This won the Nobel Prize in 2001, along with Cornell and Wyman for the creation of Bose-Einstein condensate. Now, Cornell and Wyman made the first Bose-Einstein condensate, but Ketterle refined the process significantly. Great, so we're going to go over a couple basic points. What is it? Why is it interesting? Why is it hard to make? How did Ketterle make it? What were the immediate applications? And question. All right, so first of all, what even is this? So a Bose-Einstein condensate, implies that we're going to start with a collection of bosons, which makes sense. In this case, we're going to be talking about alkali gas, which I'll give some insight on as to why in a bit. But other bosons can work as well. So there's been some work with liquid helium, with spin polarized hydrogen, and excitons, which is a composite quasi-particle between an electron and a hole in a superconductor. But all of this has been shown to work to make Bose-Einstein condensates as well. The first condition is that all of the bosons are in the same state. This doesn't have to be the ground state, but the ground state is easiest because it's really easy to just drop things to the lowest level and they'll all be in the same state. Quite recently, we made excited state Bose-Einstein condensate, which is really, really cool. And then the other condition is that the wavelength needs to be proportional to the interatomic separation. So the de Broglie wavelength just needs to be about the same size as the distance between the atoms. And so here's a little, silly diagram that we've got going on here. This is our quantum particles. Those are their wavelengths. And as we get bigger and bigger, they start to blend together and you get this indiscernible tube. So this is the equation for the thermal de Broglie wavelength. I'm sure we're all very familiar, but as you can see, it's inversely proportional to temperature, which is also great because energy is proportional to temperature as well. So if we want to get to the lowest energy state, the ground state, and we want to make our wavelength really big, we just need to make things really cold. So this is a little diagram of boson behavior as it drops to, why is my arrow gone? As we drop to about 0 Kelvin. So first, we are in the classical regime when it's hot. They act like billiard balls. Second, we start to get some quantum behavior. The wave packets start to spread out. And then we reach our critical temperature and we get this quantum soup where we get this big matter wave overlap, but there's still some non-condensed particles that are in there as well. This was predicted by Einstein in 1925, and it took us 70 years to actually make it. So why do we want to make it? What's interesting about it? The main thing is that it exhibits quantum behavior at macroscopic scales. So our sample of Bose-Einstein condensate can be quite large and yet remain like a single coherent matter wave, which is really cool because we can see quantum stuff with our eyes. There's some other interesting properties. For one, we're never going to get all of it condensed into the same state. So we end up with a mix of thermal atoms and Bose-Einstein condensate atoms, which gives us this really clear bimodal velocity distribution, which I'll show you in a second. But that makes it really easy to identify Bose-Einstein condensate in the lab. And then the other thing, which is really cool, is this is a purely quantum statistical phase transition, which means there is no interatomic interactions. One of the consequences of this, though, is that we actually have to avoid interatomic interactions, so we can't let our sample become a solid or a liquid with the exception of liquid helium. And this provides some challenges. But here's the example of the velocity distribution I was talking about. We have our thermal Gaussian, that's just gas. We know what that is. And then on the far end, we have a pure Bose gas, so all of it's in the same state, and it's really sharp peak. In theory, in an ideal gas, it would kind of look more like a Dirac delta function. But because of some weak interactions, which we can't avoid, the velocity distribution gets a little bit more spread out. And right in the middle, that's our Bose-Einstein condensate. You can just see both of them added together. So why is this so hard to make? There are 3 important requirements for creation. 1, confinement. You got to be able to keep it in the same place, and you can't use walls because it's staked to the walls. 2, you got to be able to make it really, really cold. And 3, you have to make sure that it remains a gas. And this presents a challenge because the only really way to make sure that it stays a gas is to make it not very dense. But when you make something less dense, the atoms are more spread out, which means our wavelength needs to get bigger, which means we need to get colder. So the challenge is finding a balance between density and the temperature. So this brings us to the innovations of Ketterle, 1995. So the process for making Bose-Einstein condensate that Ketterle eventually came up with was a pre-cooling stage where we get it down to about 1 Kelvin, a confinement stage where we trap them and then we compress the density just to get the interatomic separation a little bit lower, and also prepare us for the final cooling stage, which we cool down all the way down to nanokelvin temperature, so we get our Bose-Einstein condensation, and then we can study. The first step is pre-cooling, and this is actually composed of two smaller steps. And the first one, I'm just going to gloss over in the interest of time, but we get a slow atom source. Ketterle used this even slower. This just makes a beam of atoms, of sodium atoms, that travels about 30 meters per second, which is equivalent to about 1 Kelvin. We fire that into a magneto-optical trap just to hold it in place, and then we do some laser cooling. Laser cooling is really cool. We use something called optical molasses, and I'll explain the basics behind laser cooling right here. But the idea is we're using directional photon absorption and re-emission. So we have a laser right here that is tuned to just below the atomic excitation value. So if it hits the atom, it's just going to pass right through. It doesn't have enough energy to make the energy transition. However, if our atom is moving towards the laser source, that laser gets blue shifted, gets a little boost in energy, and then it can excite the atom. Once it's excited, it's got about a 50-50 chance of sending it forward or backwards. If it's in the direction of motion, it carries away some of that momentum, and our atom gets colder. If it's backwards, no net change, who cares? Now, the thing is, laser cooling is really optimized for low density for a couple of reasons. One, you really don't want atoms reabsorbing the scattered photons, because then, that's just going to slow down your cooling. The other thing is that if you have a lot of potential collisions, you can get what's called a light-assisted inelastic collision, which is when two atoms bump into each other in a circumstance that would otherwise be elastic, but because there's light, it changes some of their internal states. And if you change the energy state, then you start to have issues with calibrating your laser at the right temperature. And this brings us to something that I'm going to touch on quickly called hyperfine states. And now we should be familiar with hyperfine states, maybe not necessarily by name. But the idea of a hyperfine state is you're just splitting a degenerate state into non-degenerate states. Which usually happens with magnetic fields, and a perfect example of this is the Zeeman effect we talked about in class. This affects laser cooling. If you want all of your atoms in the same hyperfine state, because that gives them the same energy for their energy transition. If you start getting different hyperfine states, it's a lot harder. And then this is optical molasses. This is just a 6-beam configuration, lasers from all sides. So no matter which way the atom is moving, it will be moving towards a laser and will get slowed down. Next step is confinement. So Ketterle used a quadrupole trap, which generates a local magnetic minimum using 4 magnetic poles. You can see there's a dense spot right in the center. And this splits the atoms into 2 types of atoms. The first one is spin parallel, so parallel to the magnetic moment is parallel to the magnetic field. This is what's called a strong seeking state, because it will travel naturally to areas of local magnetic maximum. And then you have the opposite, your spin antiparallel, that's a weak seeking state, and that travels towards local magnetic minimum. Fortunately, because of Maxwell's equations, and we have no magnetic monopoles, we can only make magnetic minimum. So this only works for weak seeking states. So we want to keep all of our atoms in a weak seeking state if we can. This is also notable for why sodium was a good choice, is because it has an unpaired electron, which gives it a pretty strong magnetic moment. And now we encounter a problem with something called Myron spin flips. Other than being a really cool sounding skateboard trick, it is a huge problem for traps, because when you have an atom with a spin that's sitting in a place with no magnetic field, it can just flip its spin. And this means that we go from a weak seeking state into a strong seeking state, and then it just flies out of the trap. It's out of there. So this is the major source for trap locks. Now, Ketterle innovated this in a really interesting way, in a way that seems intuitive but nobody had done before, which was just plugging the hole in the middle with a laser. And Ketterle used a blue detuned laser. This exerts some optical dipole forces and just repelled all of the atoms away from the hole, which, it was really smart. This issue was also later solved with a different type of trap called the Yoffe-Pritchard cloverleaf trap, but I do not have time to get into that. And that was also after the paper was published. Great. So our quadrupole trap has two objectives. The first one, which is really obvious, is that we're just trying to keep the atoms in the same place. So we cool them down instead. But the second one is we also want to manipulate the density, because low density is really good for laser cooling, but not so good for making Bose-Einstein condensate, because it's really far apart. You can't get it that cold. And high density is really good for our next stage of cooling. And this brings us on to the final stage of cooling, something called forced evaporative cooling. Now, this is really cool. It's pretty simple to understand. The idea is you have all of your atoms trapped in a potential, really high walls. If you lower the walls, all of the high energy atoms are able to just jump out and leave, and all the low energy atoms are left over to rethermalize. Now, this works really well for high density samples with a high rate of elastic collisions. And this is another reason why sodium is good. For reasons that are way too complicated for me to explain, sodium has a really great ratio of elastic to inelastic collisions, but we can't get into calculating the scattering coefficients because that stuff's pretty hard. Hederler's real innovation was finding a way to chain laser cooling into evaporative cooling in a really effective way. And so this is a little diagram. Oh, actually, I just missed a section here. Yeah, so optical traps, we actually lower the potential, but magnetic traps use radio frequency induced evaporation, where they specifically intentionally spin flip high energy atoms, which makes them strong seeking and kicks them out of the trap. Yeah, the mechanics behind that are also fairly complicated. Here's a diagram of how optical traps work. Literally just lower the edges. Like it's such a simple concept, but so effective at cool things down. And this is our final product. This is what we came up with, and by we I mean Kettler. These two magnetic field coils make our quadruple trap. We have this laser that passes right through the hole that prevents our trap loss, and then we have a radio frequency emitter, which causes our high energy atoms to escape, so we can get that evaporative cooling. And there are the lab notes from the day that Kettler first discovered the Bose-Einstein condensate with this configuration. Great, so I'm really going to quickly touch on application because I think we're running out of time. There are three applications that I think are super interesting. The first one, obviously, visualizing quantum mechanics. We can see quantum behavior with classical tools, and this is really cool. So stuff like matter wave interference and also quantized vortices and rotating fields, which I'll show you an example of in a second. The second one is atomic lasers. You can use Bose-Einstein condensate. It's kind of like a lasing medium or one of the active mediums. But instead of amplifying light waves and creating coherent light waves, you're amplifying matter waves and creating like a larger coherent matter wave. And so you need a source of mass, because obviously we can't just make it out of nothing. So you can pass a matter wave through Bose-Einstein condensate and it will pick up some of the mass and create more matter waves that are coherent with the incident wave. And then the last one is some gravimetrics. This is really cool because we can see that interference. If you drop two clouds of Bose-Einstein condensate right next to each other and they travel at different speeds, you can use it as an interferometer to measure gravity. Now, quick visualization, that's an interference pattern. That is like very intuitive for us as physicists, but it's also kind of crazy because you're taking two atoms and you're putting them on the same spot and they disappear. What's up with that? And then the next example of the quantized vortices, if you don't like a lot of little tiny holes, you could look away. But these are the quantized vortices. So when you rotate the Bose-Einstein condensate, obviously you can't have, there are discrete amounts of rotation that you can have. So instead of forming a big continuous rotation, you get a bunch of tiny little rotations. And that looks really cool and it's super interesting. So overall, we learned what a Bose-Einstein condensate is. We learned why it's interesting because it lets us study quantum mechanical behavior. We learned why it's hard to make, chaining together laser cooling and evaporative cooling, and that was the innovation of Kettler. And then we talked a little bit about applications. Great. How did I do on time? All right, awesome.
Okay, thanks. Okay, I have two questions for you.
Yes.
My first question is, in the famous plot of this is what a VEC looks like versus a thermal state.
Yeah.
What is plotted on the vertical axis?
So I think in this case, this is just the amount of atoms that are in that. Like this is if we cut this sideways, we get our two-dimensional Gaussian distribution, which is what we expect. Like that's just how we look at thermalized atoms in general. So it's like what proportion of atoms are in what velocity state, right? Show it as continuous. But this is just in 3 dimensions to show the x, y, like the two-dimensional nature of velocity.
Okay, thank you. In the evaporative cooling step, you had a bullet point that says the atoms are continually thermalizing.
Rethermalize. Yeah.
And so you want to minimize interactions.
Well, in this case,
Yeah.
We don't want to minimize collisions.
Okay,
We want to maximize collisions, and that's
Good.
part of why we want to increase the density of the stuff,
I see.
because that lets them kind of reach thermal equilibrium.
Okay. Do you know what the time scale is for thermalization? Like,
Yeah, so for sodium, for like it depends on what material you're using, but in this case, the rethermalization time for sodium atoms or alkali gas can be as long as like 1 to 2 seconds, which is really long, which is why we need to really, really minimize trap loss as much as possible. And that's why plugging the hole with the laser was super important, because previous work by Cornell and Wyman produced Bose-Einstein condensate, but was significantly less. Well, there was significantly less of it, and it took a really long time. So Ketterle's work produced Bose-Einstein condensate with 200 times as many atoms as the previous work, and produced it 40 times as fast. Okay. So major strides in the creation of Bose-Einstein condensate, and that's why he was included in the Nobel Prize.
and last question, where was the first Bose-Einstein condensate in Canada made?
In Canada, was it here?
Yeah, in this building.
Yeah, I read a paper this morning about that.
So that was Professor Van Weingarten's work.
Yeah.
Right after this. Cool. Okay. Other questions for Cassia? Okay, thanks again.
Great. Yeah, thank you so much.